Good afternoon and welcome to MAE 113 Calculus for the Liberal Arts. My name is Richard Kohar and thank you for tuning in on this Tuesday afternoon. Today's lecture is number 28, Mathematical Models Using the Exponential Function. Again, probably before I go too fast, make sure that my audio is good. Again, give me a thumbs up, something in the chat to show that it's working. Hopefully, we'll see. Excellent. Okay, excellent. And quiz marks coming in. Looks really good. Yeah, they're really good. Wow. Either I'm making the questions too easy or you guys are studying. So hopefully that's good news. We'll see. We'll have a look. I'll have to check through the marks afterwards to see what was kind of missed. But looks good. Yep, fingers crossed. No, they look good. It's, yeah. Again, I don't like talking about marks online, but yeah, they look really good. So, right. So today we're going to kind of go through this. So, mathematical modeling of this particular kind of situation is, we see this in like biology, in chemistry, in physics, in economics and business, that there's certain quantities that grow or decay at a fixed rate, and that rate is proportional to their size. Now, we can kind of set up this idea. So we have some original function, y is equal to a function of time. So it's the value of y at time t. And if the rate of y with respect to t is proportional to the size of this at any time, then we can actually rewrite that. So again, just transforming what we've said in words into mathematical notation, we have the change of y with respect to t, and this sign right here is proportional. Excuse me, proportional. So I've written it in Leibniz notation, and as well as over here, this is like with the prime notation. So over here, when we have a proportional, and again I have just this y, when we say something is proportional, it means that there's to put in an equal sign, something like this. So to replace that, you need to know a constant k. So it's some sort of number that will make this equal. So that's a fixed value. So it's a fixed constant to make that true. So let's say that we'll make this k. So we'll say that constant is k. Then, again, I can just switch this. Instead, I have the proportional sign. I'll make this equal, and we'll have it k times the y. And same thing over here. I'll have the f prime here. This is using the prime notation. That'll be equal to k times the original function. So there we go. So I have the derivative of y with respect to t is equal to k times the original function y. Or I can write this using the prime notation. F prime is equal to k times the original function. Just as a little note over here, this is probably your first differential equation that you will see. And what we're interested in now is we know this relationship that the rate of change of y with respect to t is equal to some constant times the original function. Now, just two little things again. If k is greater than 0, it means that it's going to be growing. So again, it's some positive value, which means it's going to be multiplying the function itself. And so that means that it's going to grow. So we call that the law of natural growth. And similarly over on this, if k is less than 0, that means that this would be a negative value, and that the next value of y will be less or negative. So it's a negative growth. So you can also call it the law of natural decay. Now, we're going to try to solve this. And, of course, to solve y equals f of t, it requires solving this. And can you think of a function whose derivative is a constant multiple of itself? I'll just give it some time. What function is a derivative of itself times, well, we've seen this previously. Mr. Walker, of course. Yeah, it's the exponential function, exactly. And thank you for pointing that out. Good job, because it's the title of course, for our lecture. So we're going to use the exponential function. So, let's move on to number 2. Come on, ink. Okay. So, we're going to use that original function. So I said we're going to use that exponential function, right? So that's going to be our guess. And we're going to show that that's true. So we're going to say that we're going to let y equal some constant. So we'll say c some constant e to the kt. So that's what it's going to look like. So what I'm going to say that this is kind of our initial guess, and then we'll also show that this will work for our equation that we want to prove. So we're going to say that C0 or C0 is a constant. And then I'm going to take the derivative of this. So dy by dx. Oh, I'm going to use by dt in this case because it's with time. So I just leave the constant alone. And then I'm going to take the derivative of this. So we know that the derivative of e is just itself. And then I still have to take the derivative of the inside function. So again, taking this with respect to with t. So again, I'll just kind of write out an extra step here. Times k. And I'll just rewrite this just a little bit nicer. So I'll write the k, I'll just bring the k out front here. And then I have C0 e to the kt. And the nice thing about that is y. So what we have shown then is that the derivative, or the rate of change of y with respect to time, is equal to k times the original function at t. And of course, I can also rewrite that as over using the other notation. I can also write it as f of t is equal to C0 e to the k of t. Oh, yeah. And same thing over here. Then that is equal to k of f of t. Now, so what we have shown then is that the solution of this differential equation that we had is y equals c of naught e to the kt, where c naught is the initial value. Oh, I'm saying the initial value because if we go back here, if you note that if I put in f at 0, which is this kind of starting at time 0, then I would have c naught is e to the k, and the t is 0 right here. So I'll have c naught is equal to e to the, this becomes 0. And we know that any base to the 0 is 1, which means that I'm left with c naught. So that's how we get that f at 0 is equal to c naught, or c0, and that's why we call it the initial value. So there's lots of things that we can see in nature, in business, where we can have things growing proportionally to its size at any time. So for instance, in a bacteria culture, the growth is a result of the bacteria, and the more bacteria present at a given moment, the greater the opportunity for cell division. And this reasoning is valid under ideal conditions where there's adequate nutrition, there's freedom from disease, unlimited environment. Again, we're going to assume that there's kind of like an infinite petri dish and it can keep growing. So we had looked at this previously when we were looking at the exponential function. So we'll return back to this idea. So again, like we're going to look at bacterial growth. Bacteria growth. And again, these are under ideal conditions. Which means that there's like enough food, space, other freedom from other competing organisms. So that's kind of bacterial growth. So we'll just make those assumptions. So here we go. So here we go for number 3. So here's the example. A bacterial culture starts with 2,000 bacteria, and after 3 hours, the estimate count is 10,000 bacteria. Then, for part A, it says find the number of bacteria after t hours. We have B, which says find the number of bacteria after 2 hours. C, find the rate of growth after 2 hours. And then D, when will the bacteria population reach 18,000? Okay, so I'll switch to just a blue pen for this. So for A, what we're going to start off with is we're going to say, we're going to define our function. So we'll say that we have our y at f of t is the, not the pound sign, it's the number of bacteria. after t hours. Okay. Now, from this, we're actually told right here that we're starting out with 2,000 bacteria. So part of our given information is that our C0, which is F at 0, is equal to 2,000. And the other thing is that we're told that at 3 hours, the estimate count is 10,000. So we're also given F at 3 is equal to 10,000. So what we have is we're using our solution. So we know that our solution is of the form y equals c naught e to the kt. So I'll just kind of write that over here again. What we'll do is we'll replace our c naught now. So we'll say that it's going to be, we have f of t is equal to 2,000 e to the kt. So we were able to specify what our C naught is. The other thing that we need to do is figure out what our growth factor is, which is the K. So now we need the growth factor. Or the growth rate. Oh, sorry, growth factor, K. So we use this part of the information right here. So we know that at f of 3, that's equal to 10,000. And that has to equal then the original, this function over here. So 2,000 e to the kt. And this is why we were learning how to solve equations with kind of the exponentials. So we have this. The next thing that I need to do, well, what I can do is I have 10,000, I have 2,000. So let's just get rid of this part right here. So that cancels and this cancels. I'm left with this and these cancel. So I have 10 divided by 2. So that equals 5 e to the kt. Now, has anyone noticed that I've made an error? Where in here? There's something. I'm trying to solve for k, but what piece of information should I have entered in? Yes, that's right. Wouldn't it be 10,000 equals 10,000 times, I'm assuming the x is the times e to the 3k. That's right. So over here, so we'll just kind of, there we go. I'll put it over on this side, like that. Good. So we still have to solve this. I still have k in the exponential. And the way that we'll do that is I'm going to apply logarithms to both sides. Now, because this is e, I'm going to pick my logarithm base. That's going to be nice. So I'm going to pick my logarithm base to be e, and that's going to be ln, right? So again, remember that ln is equal to log to the base e. So applying ln to both sides, and then I'm left with ln 5 is equal to, now because of my rules of logarithms, I can actually take this right here and bring it down in front. So I have 3k times the ln of e, and we know what the ln of e is. What is it in the chat? Ln e, we just did the quiz. Some of you might have had that question. Someone would have had another question. But what's this ln e? One. Yep, good. Excellent. Yep, and the reason for that is, again, right, we have log. What happened to half? Nice. Yeah, we have log to the base e of e. So again, that is equal to 1. Yep, exactly. Log to the base b of b is equal to 1. Yep. And if you don't believe me, let's pull out. Here's a calculator. I'll put in 1, and I'll apply the logarithm, the natural logarithm there, and that's, oops, no, that gives me 0. So I did ln of 1. So I need to do ln of e. So 1, there we go, 2.7183, and then we'll take the ln of it. That gives me 1. So that is equal to 1. So now I have ln 5 is equal to 3k. And then I can bring this over to the left-hand side. So I have ln 5 of over 3 is equal to k. Or some people might write that as k is equal to 1/3 ln to the 5th. So that's good enough. You don't have to calculate that, but if you really were interested in what that rate would be, we have 5. We're going to take the natural logarithm of it and divide by 3. So that is approximately 0.5365. So putting that value back into the original function, so therefore y equals f of t is equal to 2000 e to the 1/2 ln 5 times t. What else can we do? I can also kind of rewrite this a little bit nicer. So I can have ln of 5 times t to the t over 3. So all I've done is I just taken that fraction, that third, and moved it over with the t. And what else can I see right here? Well, e to the ln of 5 is just 5, right? Because again, e to the ln of x, because it's the exponential, and the inside of that is its inverse, which is the ln. So that is just equal to x. So in this case, this is just equal to 5 to the t over 3. Perfect. So we can return to our next part, which is find the number of bacteria after 2 hours. So I think it means at 2 hours. So let's do at 2 hours. So at t equals 2 hours, we'll just substitute in our value. So we just use f of t, or t is equal to 2. So f at 2 is equal to 2,000 times 5 to the 2/3. And I wish I could make that any nicer. Nope. So we can pull out a calculator. So this is kind of a nice number that I'd expect on an exam. You don't need to use a calculator any further, but we'll use 2/3. Maybe I'll put in my base first. Sorry. My base first. And taking the exponent, I get 2.92, and multiplying it by 2,000 gives me approximately, I'll just round to the nearest whole number, 5,848 bacteria. Cool. All right, now we were asked to find the rate of growth after 2 hours. So this is page 4. Rate of growth after 2 hours. So for part C, we already know what, we have our original function, so we have y equals f of t is equal to 2,000 e to the 1/3 ln 5. Sorry. There we go. Just to make sure that that's my original function. Perfect. So this is asking us what is the growth, the rate of growth. So that just means what is the derivative? So to find the rate of growth, we'll take the derivative of that. So we have the 2,000, which we'll leave alone, because that's our constant multiple. Then the next part is we'll just have to deal with taking that derivative. So I'll just kind of take it as a step. So I know that I have my constant, and then I take my derivative of this function. So e to the 1/3 ln, just like that. So we're going to take the derivative of that. So again, the derivative of, I'll use d by dt, e to the g of t is equal to e to the g times the derivative of g. So this is kind of my g function right up here. So e to the e to the 1/3 ln 5th times t. And then I need to take the derivative of the inside of the function. So again, this is the g right here, times. So 1/3 ln 5 is a constant. So again, if you wanted to see that, here's 5, so ln 5 is 1.6094, and divided by 3 gives me 0.5365. That is a constant. So in here, right here is a constant, and then I have t. So when I take the derivative of that, I just need to take, I have the third ln 5 times t. I only have to differentiate with respect to t. So here's my t, and there's my constant. So the derivative of this is just 1/3 ln 5. Times 1/3 ln 5. And then to finish off what they were asking for, they said to find the rate after 2 hours. So we'll assume at time equals 2 hours, that dy by dt at time equals 2 hours. So again, that little line means evaluate. So evaluate at t equals 2 hours. So we just substitute in and that's good enough. Now again, if you had a calculator, you'd pull it out and we would plug this in. And let's see if I can do this. So I have a third and I have a ln. So right here is 1.6094. Up here, I'm going to multiply that by 2. So I have up here is 3.2189. I'm going to take the exponential of that. So there is 25. I'm going to multiply it by the 2000. So there is 500,000, or sorry, 50,000, and we multiply it by the last part there. So, oh, did I miss? I must have mixed up something. It's getting too big. I'll even switch over to this one. There we go. 2,000 times e to the 1/3 ln, times ln 5 times 2 times ln 5 divided by 3. There we go. Much better. So again, remember that this is a rate. So we have a dy by dt. So it's the number of bacteria over time. And in this case, it's the number of bacteria over time, which is bacteria per hour. So at t equals 2 hours, we are expecting roughly 3,100 bacteria per hour, which is, you know, it's growing. We have one last little question to finish. It says, when will the bacteria population reach 18,000? So, d. So when is the population 18,000? So then that just means that we take our formula. We have 2,000 e to the 1/3 ln of 5 to the t equals 18,000. And I can divide by 2,000. So that goes to 1, and I can cross out the 3 zeros. So I have 18 divided by 2 gives me 9 e to the 1/3 ln of 5 of t. And same idea again. We can apply the logarithm, the natural logarithm on both sides. So that means we can take this, move it in front. We know that that's equal to 1. And then I can bring this over to this side by dividing it. And I have the 1/3, so because that's in the denominator, I can bring that up top. So that's just 3 ln 9 over ln 5. And again, that's good. Don't have a calculator, that's good enough for us. Let's see if I can remember how to use this one. I'm going to have 3. I'm going to take the logarithm of 9, multiply that. So that's approximately 6.5 on top. And then I have ln of 5, divide that by to get approximately 4. So that means that the population will reach 18,000 bacteria after 4 hours. Is that okay so far? We spent all the time, learning those rules for logarithms and manipulating it so that, again, now that we have e when we're using it for exponential models, we can actually solve now for t or k or c naught to figure out what those values are. Questions, comments? Excellent. Okay. So in this case, oh good, it's nice to put them to use. Yeah, exactly. I know. It's hard because sometimes you need to learn some of the skills and then the applications come along, and then sometimes you have to go back and it's hard to understand why you're learning a skill if you don't have the application, and sometimes learning the application itself is hard enough without knowing the skill. So it's kind of cyclic. You have to learn the skill, look at the application, then go back and learn the skill, and then try the application again. Now that you understand why we're so trying to get that skill in the first place. So it's hard because you can't. It's cyclic. A practical use, I mean, yes. Well, okay, so we're still kind of. I know that most of you are business and economics, so we'll get to that eventually. Because I'm going to show you just we saw a simple growth model. We can do a decay model, which we see in radiation, or when we're talking about radioactive substances. So there's things that we have a half-life of a radioactive substance, and the half-life is the period of time remaining during which any given amount decays under half of its remains. So maybe I should have, so we have the half-life, but just as like a little background, so like half-life. Of a radioactive substance is the period. And of course, you know that at RMC we have a nuclear reactor. It's not designed for producing energy. It's designed to do analysis of samples. But we have the Slowpoke 2. And I can't remember how many in Canada that we have, but it's one of a few. And if you're walking along in Sawyer, you'll have seen Module 5 that you would have seen it. So the half-life of polonium-210, so 210 meaning that it's the isotope, is 140 days, and a sample of this element has a mass of 300 milligrams. We're asked to find, for part A, the mass that remains after T days. Yep, that sounds about right. 14 toasters. Yeah, a couple of light bulbs. Yeah, it's just designed to do analysis for samples. For part A, it says find the mass that remains after T days. So basically, we'll say, well, first of all, we'll see that y equals f of t is the mass of the sample. And we'll say that it's in milligrams. And remains after T days. And polonium is decaying quite quickly. 140 days, because again, like we have half-life of other samples when we do carbon-14, which is used for carbon-based dating, is something like in the realm of like 5,000 years. So, which is helpful for when we're carbon dating. We're trying to date how old something is, assuming that it was a natural organic substance. So yeah, we're given some information. This up here, so the half-life is 140 days, and the sample of this element has, so this is the, here's an important part. So we have 300 milligrams. So at time 0, that's equal to 300 milligrams. And so far what we have in our function is, we know that this is our C naught, or our initial value, so it's 300 e to the kt. And we also need to determine k. So to figure out k, we have one more. Do we have one more piece of information? That the half-life is 140 days. So this is where we have to yes. Perfect. You guys are ahead of me. Excellent. Okay, so that means yeah, exactly. So f at 140 days is 300 divided by 2. 30 divided by 2 is 15. So I tack on the extra 0, so that's 150 milligrams is left. So I know that I have 150 is equal to e to the, sorry, I should also put this at f at 140. And at here I'll have 300 e to the k times the time. So I'm just going to write the 140 first and then the k. Okay, then the next thing I can do is I can divide by both sides by 150. Or, no, I'm going to get rid of this 300. That makes it a little bit easier. So then I'm left with e to the 140k. And on this side, I have 15, well, I have 15 divided by 30, or that's equivalent to 1/2. And then I do the same thing. I have to solve for this. So to solve for that, I'm going to apply the logarithm. So I do ln of 1/2 is equal to ln of e to the 140k. And I can bring that down front, so I have 140k ln e. Again, that's 1. So I'm left with 140k ln of 1/2. And I can divide the 140, so ln of 1/2 time divided by 140 of k. And I'm just going to neaten this up just a little bit, because I have ln to 1/2. So just, maybe I'll switch pens here. So ln to the 1/2 is equal to 2 to the -1, which means then that I can bring that -1 down in front so that I get minus ln of 2. So everyone's okay with that? 1/2 is equal to 2 to the -1. And so I can bring that down in front, that minus, and I have negative ln 2. So therefore, k is equal to negative ln 2 over 140. And that's approximately equal to, so again, you can just leave it like that. That's good enough, ln 2 over 140. But if I take it into the calculator, approximately 0.005. So we're almost finished part A, so therefore f of t is equal to 300 e to the minus ln 2 over 140 to the t. So that's our equation. I'm just going to rewrite that again. Just up top here, f of t is equal to 300 e to the minus ln 2 over 140 of t. So that I can go back up to the top here. And then I'm told, find the mass that remains after 50 days. So B, we're going to assume that it's at 50. So at t equals 50 days. That just means plug in the number. So plug in 50 into this. So I got 300 e to the minus negative ln 2 over 140. And I have t, which is 50. So I'll plug that into this. And 50 times, take the exponential of that, and times 300. So that gives me approximately 2 milligrams left. I just also like to point out that we have our K is equal to minus ln 2 over 140, or you can think of it as negative 0.005. And it's that negative. So when, again, K is negative, then we know that it's a decaying rate. So again, going back to this, we had K is greater than 0 and K is less than 0. So K is greater than 0, and that means it's growing, and negative or less than 0, it means that it's decaying. So again, when we had our example here of the bacteria, the K was positive, which means that it was growing. And in this case, we have the K is negative, which means that it's, decreasing over time. So we have the mass that remains at 50 days. So we finished that one. Then we're asked to find the rate of decrease of the mass after 50 days. So at t equals 50, and rate of decrease means find the derivative. So we can take the derivative of this. So f prime at t is equal to, and we'll take the derivative. We have 300. So again, I don't touch that constant. And I'm going to take the derivative of the outside function. I'm using chain rule. So again, my e here. So I'm going to leave everything alone. And now I need to take the derivative of the inside. And again, this ln 2 over 140 is a constant, and I just have to take it with respect to t. So t, we only have 1 to the degree 1, so that just means that that is going to be, my derivative is negative ln 2 over 140. And then, so we have our derivative, or our rate of change, or sorry, our rate of decrease. And then we're asked to find what the rate of decrease is at 50 days. So we just substitute that value in, 50. Times 50. And if we substitute that into a calculator, what would we get? I'll pull out this one. Let's try this one. So I'll get 300 times, let's go E. Oops. E to the minus ln 2 divided by 140 times 50. Close the bracket, times ln 2 divided by 140, and that is approximately equal to negative 1.1, let's go 1.6. Now again, we have to remember that this is a rate, which means that this is and this is why the prime notation's not, I'm not a big, it doesn't lend itself nicely to this. If I did dy by dt, we know it's the quantity with respect to time. So in this case, it would be the amount of milligrams with respect to days. So it would be minus 1.16, yes, exactly, milligrams per day. Exactly. And then we have D, which is, they're asking us how long will the sample take to decay to a mass of 200. So how long? So time equals question mark to get to 200 milligrams. So we have 200 milligrams is the amount that we want to get to. We have our function, e to the minus ln 2 of over 140 times t. And what's the next thing we can do? We can divide by, let's divide by 300, get rid of this side. So, oops. So that goes to 1. And on this side, I'm left with 2/3 is equal to e to the minus ln 2 over 140 times t. And then I'm going to apply the logarithm on both sides. So ln of 2/3 is equal to the ln of e to the minus ln over 2, ln 2 over 140 times t. Again, that comes down in front. So down in front here, ln e is equal to 1. So I'm left with negative ln 2 over 140 times t, ln of 2/3. And to solve for t, oh, I should have bring that over to this side, ln 2 over 140. So that gives me negative 140 ln 2/3 over ln 2. So that's the kind of the answer that you would give me, because you'd say, oh, well, I don't have my ln tables. So that's good. 2/3, we'll take the ln of that times 140 to, so this is approximately equal to 81.89. And again, the time that we're working in is in not hours, it's in days. Okay, so now we can move on to, let's do some compound interest. Switch over to a black pen. A bold black pen, because this is important, right? Because this is for, now we're at the compounding interest. Again, this is, you know, in terms of saving or investing, usually you'll have like some sort of amount of money, set money that you start out with, called usually the principal. And over time, that should grow at a certain rate. And again, it's, you take the original amount and you're multiplying it by that rate K. So I'll write that out. We'll have some sort of like money. So you'll have some sort of P, which is called the principal. And that's kind of like an amount of money. We say that R is the interest rate. Interest rate. Okay. And after one time period, what we have is P of R. So that is the interest. That's what we'll call, like, that's the amount that you've kind of earned. And then the total amount of money that you've got. Be careful, Warren Buffett is watching. Yes, should always, yeah, the power of compounding. And the amount of money is, so they'll use kind of like this amount, they'll use A. So it's equal to P, so it's your original amount, plus the amount of interest that you've earned, so PR. And we can factor out that P so that I am left with 1 plus R. So for example, if I had, my principal was $1,000 and the interest rate, you know, let's pick something like in a stock or a mutual fund or something like that, which is follow something like 7% per annum, which is definitely not what the current interest rates are on savings accounts. Wow. Anyways, the interest rate will say 7%, which means then that R is equal to 0.07. So the way that you get the percentage is you divide by 100. That means that after 1 year, that would be 1,000 times 1 plus the interest rate, or 1,000 yes, but my interest, yes, yep, giving just better than 7. Yeah, that's why I picked 7. 7 is kind of standard. And if you pulled out the calculator, 1.07, and you multiply by 1,000, you should have 1070. Of course, you just had to move the decimal places, but now the compounding part. If you take that interest, so if you just left that alone, so you had the 1070, it was in an account. Again, it could be in a margin account, it could be in a savings account. You just left it and you allowed it to reinvest. Okay, so just that's the end of that. If you don't touch it, and I mean, you don't touch it, I mean, it's quote reinvested. Reinvested. The new principal would be, you'd have 2 periods. So you'd have P times 1 plus R times 1 plus R. So again, that would be for 2 periods. 2 time periods. And if you did it for 3, you'd have P times 1 plus R to the 3. And so you can understand if K periods, then you have the amount is equal to the principal times 1 plus R to the K. Oh, sorry. I didn't see the, I have an acquaintance who uses an investment broker and is earning 20% this year. The market seemed to be a little strong at the moment. Yep. They're doing well. Okay, yeah. Nice, got his number. So we have this. What happens is that sometimes instead of just using, instead of compounding annually or per annum, or sorry, annually, you can compound at different, sometimes it's not annually, sometimes it's like semi-annually, you'll get your interest rate or your interest paid out, or you could have it quarterly, like dividends. Dividends is usually handed out at like, well, gotta be careful because this does not include our dividends as well. But everything also fell. Yeah, it all, yeah. I wish I could predict the market a little better. Otherwise, we'd all be a little bit richer. Instead of compounding annually, we can have it like, again, semi-annually, monthly, daily. So, for instance, if I had, let's say it was 7% per annum. Per annum. Again, annum, Latin for year. So 7% per year, but we're going to be paid out semi-annually. Then that means that I can do that over 6 months. And the interest rate then is, so we'll say that it's 0.07 over, we'll divide that by 2 because there's 2 payments in a semi-annually. And that would give me 0.035. I think that's right. Perfect. So in general then, if I had my interest rate, so I had my interest rate was R per annum, compounded, n times, then the number up here, this K, would be my R over N, the number of times it's compounded. So then from that, that means I have, so just kind of going back to my original equation here, I had A equals P, the principal, times the interest that I've earned, and I get that K times. Well, this K is going to get replaced. So that K gets replaced by my, the number of times I'm going to compound. So if I compound, it's per annum n times, and I have it for t years. So it's n compound per year. And I have t is the years. So that gives me my t. Then up top here, the number of periods that I'm going to have is going to be, K is going to be n times t. And my interest rate is going to be R over N. Oh, I keep missing it. It's a firm, it requires large minimum investment, and it doesn't cut it. Well, let's kind of work through an example then. Let's say that we don't have a ridiculous amount of money to throw around. Let's use an example here of just $1,000. And again, if you go onto some of those market watching websites, they'll say like, here is $1,000 and this is what it would have done over like 5 years, 10 years. You would see it kind of like grow or decay, and you would see that. What we're going to do is we'll say that we'll have a sum of $1,000 again, and we invested it, And let's say that it has 12%. We'll say it's guaranteed per annum. Find the amount in the account after 3 years. If the interest is compounded annually, semi-annually, quarterly, monthly, and daily. The power of compounding. Okay, so again, what's my given information? Again, I'm starting out with $1,000. I have an interest rate of 12% per annum, and I need to know it after 3 years. So again, the principal is $1,000. My interest rate per annum is 0.12. And I'm going to have it after 3 years, so my T equals 3 years. So for A, if it's annually, that means the number of compounding periods in a year is 1, which means that my amount that I'll have at T equals 3. So I start out with the $1,000 amount. That's my principal, plus my rate of interest, which is 0.12, and it's divided by the number of compounding periods, so that's the N1. So again, it could be just simply written as 1.12, and that's nice because it's 1,000 times 1.12, so it's 1120. Now that's in the first year. What they want is they want it in the third year. So in the third year, it's going to be 1,000 times 1.12 cubed, because it's going to be n times t, which is 3 times 1, which is still 3. So 1.12 cubed, 1.4049 times 1,000 gives me $1,404.93. Okay. If it's compounded semi-annually, so that means that it's going to have 2 within a year, then my amount, again, after T equals 3 years, I have 1,000 is my starting amount. 1 plus 0.12 divided by 2, and then 2 times 3. So let's simplify that. 1 plus, and then I have 0.12 divided by 2, so that's 0.06. 2 times 3 is 6. And I'll bring out the calculator. Whoops. 1.06 to the 6 times 1,000 so I get 1,418.52. So you notice I got a little bit more interest than if I compounded semi-annually. Perfect. Excellent. Excellent, excellent, excellent. So hopefully it's using what we're using here is the same formula. Same thing. If it's quarterly, it means that I have 4 time periods within the year. So n equals 4. Again, my still 3 years. I have $1,000 I'm starting out with. I have my interest rate is 12, which is going to be divvied up over 4 quarters. And then I'm going to have 4 quarters times 3. So I have 12 divided by 4 gives me 0.3, so 1.03. 4 times 3 is 12. And I'll pull out the calculator again. 1.03 to the 12 and multiply it by 1,000 gives me 1,400 and yes, perfect. So you can do the same thing again for D. So again, n would be equal to 12. So I would have 1,000 times 1 plus 0.10 divided by 12 times 12 times 3 years. So that would be 36 periods that I'm getting at. Same idea, so it should be 1,430.77. And we'll finish off. We'll do the daily, so that would be 360. We're going to assume it's 365. We're not going to use a leap year. So if it's compounded daily, I'm going to assume it's 365. Could be 365 point a quarter or something like that, but same idea. Dividing that by 365. I have 365 in the year, and I'm going to multiply by 3. And again, just plugging that into the calculator gives me 1,433.24 cents. So again, you can see the more periods that you're getting compounded, the more money that you get. So we see from this example that interest paid increases as the number of compounding periods n increases. So let's just make a note of that. So the interest paid increases as the number of compounding periods n increases. Okay. So what if we let n go to infinity? That'd be nice, wouldn't it? We could have infinite money. So what we'll do is this. I have the amount, so I have P is equal to 1 plus, I have my rate over n, which is my number of compounding periods in a year, to the number of compounding periods in a year times the number of years. And what's the next thing that I will do is I'm going to say if we let, for instance, if I let m equals n over r, so if I do that, I get I'm just doing a little bit of manipulation here. Why I did this is because as I want this is what I wanted. We recall when we were looking at something, if I look at this, say 1 plus 1 over m to the m, this actually approaches the number e. And what I mean by that is if I have the limit as m goes to infinity of 1 plus 1 over m, that equals e. So what I can actually do now is that is the number of compounding periods goes to infinity. This amount approaches the amount is equal to the principal times e to the RT. And usually you'll see something like this. This will mean that the interest is paid continuously, is paid or compounded continuously. Which would be nice. So again, instead of sometimes if as a quick calculation, sometimes maybe we don't have enough time to figure out how much what the daily compounding, or you know if we wanted to do something like quick off the cuff kind of back of the envelope calculation. Again, if I had that same $1,000, this is the principal, and I invested it at a rate of 12% per annum, and it's compounded continuously, well, that means that I can use this formula, the 1,000 times e to the 0.12 times, oh, and I need to say how many years I'm going to do this for. Oh, yep. I have to also say that this is for 3 years. So for 3 years, so I have 1,000 times e to the 0.36, and that is equal to, and I'll pull out the calculator, 0.36 to the e, and now multiply by 1,000 gives me $1,433.33, which is kind of nice because if I go back to my number of compounding per day, it's pretty close. I'm only off by 9 cents. So again, if I wanted something quick to do, I can just use this formula. So the principal times e to the annual rate, or the annual interest rate, times the number of years will give me approximately what I would get if I was compounding daily. So again, comparing what I did, comparing to the calculation of compounded daily, I had $1,433.24. So I was only off by $0.09. So we covered a lot of material in this mathematical modeling using exponential functions. What we found is that we looked at an interest rate problem. We saw that we have compound interest. We can look at that where we can have half-life of a radioactive material, and we can also look at bacteria culture. There's lots of things that we can actually again, those are kind of two growth and decay are kind of, the nuts and bolts of the exponential modeling. The other two ones that we can use is something called learning curves, and the other one that we'll look at is a logistic curve. And those are where we actually introduce horizontal asymptotes so that we don't have kind of that issue where something is just continuously increasing. This is kind of the exponential. And again, another exponential or an exponential decay. So this is exponential growth. And this is exponential decay. But sometimes what we want is maybe something like this, where it actually will approach it. And those are some things like learning curves or logistic curves. And again, that's where we have kind of a horizontal asymptote. And we'll get into those next time. Again, questions, feel free to send me an email. I will post an assignment later tonight so that we can start working on some of these questions. Again, feel free to send me an email. And on Thursday, again, we have office hours after our lecture at noon from 12 to 12:50. We also then have, I have hours from 1 to 3. And if you have, you can make those times, again, feel free to send me an email. We can set up an appointment, as well as the Math Help Center is available through Moodle. Thank you everyone for tuning in, and I will see you on Thursday. Oh, will there be a quiz next Tuesday, given that there is no Monday class? I will have to check on that. That is a good question. Yes, we have the holidays coming up. That is a good question. I will get back to you on that. Thank you. Have a good night.